Hello, it's time for the 2.3 video lecture on conditional probability and independence. All right, so this is actually really useful and I think pretty interesting. So a lot of times when you're calculating probability, you already know something about a situation, and that's called conditional probability. So you'll see this symbol here, probability of A given B. That means this B stuff, we already know this happened, all right? Or we already have some information about the situation. So this is the probability of A given that we know B has occurred, or we're just going to say probability of A given B. The formula for this you can find, because you should be writing notes for all of 2.3. But it's going to be the probability of the intersection of A and B given, over the probability of the given event B. All right, so this is the thing you need to know, right? Like, you'll probably remember the intersection, but it's the probability of the thing that was given. All right, here's kind of why. Like, if we have, let's say we have the juniors in our class, we'll call that J, the event that somebody's a junior, and we'll say F is the event that somebody's a female. And if we had, so we have all our females here and our juniors here. All right, I just want you to think about this. Here's F intersect J, right? If we wanted to find the probability that someone was a junior given they were a female, let's just think about it. What we would do, we know they're a female, so what that would do is restrict us to just being inside this circle, right? But so we want to know what's the probability they're a junior given they're inside that circle. Well, the only juniors in that circle are in the intersection, right? So what it does is it just kind of changes the sample space. So what I'm trying to show you, I think you're noticing hopefully by now. I really want you to understand things. If you understand them, then you won't just be relying on formulas all the time. All right, so the probability that somebody's a junior given they're a female, well, we're stuck in the female circle, right? So that's kind of like our sample space. So it's just this percentage of people out of the percentage that are in the female circle, right? So the juniors who are females over the probability of being a female. So that's kind of why the formula works. Because of that formula, you can get the probability of an intersection of two events two different ways, based on which one you were conditioning on. Okay, so it's either the probability of A given B times the probability of B, or the probability of B given A times the probability of A. That's just by multiplying both sides by the denominator in those formulas. So these are really useful formulas too. All right, let's look at kind of an example of this. And I know I just use a Venn diagram to demonstrate this, but I'm going to start demonstrating a different diagram that's really useful in conditional probability, and it's a tree diagram. And you'll see that these formulas especially are really helpful on a tree diagram. Okay, so tree diagram. All right, so this is a real typical kind of probability problem, but when we come to class, we'll have an example that has diseases in it, so it's more of an applied problem. But we'll start really simple. A bag contains 2 dimes and 3 nickels. I usually make like a little picture, 2 dimes, 3 nickels, and we're drawing 2 coins randomly out of this bag. And we want to find probabilities about this situation. Here's how you're going to, one way you can diagram this. You really should diagram it this way. This is called a tree diagram. This is the beginning right here. We start here, and we're going to go down one of these paths, and this is representing the first draw. First coin that is drawn, and we know it can be a dime or a nickel. Dime or a nickel. And the probability that it's a dime would be 2/5. I'm going to write that probability right on here. And the probability that it's a nickel would be 3/5. In a second, we'll label these. So I left some space here to add some labeling. So if you're doing this too, you probably want to add some labeling in a second. So depending on which way we went, I'm going to call this dime sub 1. So on the first draw, I got a dime. So now this second set of branches represents the second draw, the second coin drawn. So notice if we had a dime on the first, we could get a dime on the second, or we could get a nickel on the second. Or if we came down, if we got a nickel on the first, we could get a dime on the second or a nickel on the second. All right, so let's find the probabilities of these. I'm going to go through this quickly. You can slow this down and think about it. I hope you will. If we got a dime on the first, then we already took one of these out, right? So we would only have one dime left, and we would only have 4 coins left. So the probability of having a dime on the second would be 1/4. But the probability of getting a nickel on the second would be 3/4. Notice I've left space on the left of these to add labels. Similarly, if we got a nickel on the first, then there's still 2 dimes left, but there's only 4 coins left in either case. All right, so let's think about this. This would be this. We could write the probability of getting a dime on the first is 2/5, and this is the probability of getting a nickel on the first. But let's think about this one. Is this the probability of getting a dime on the second? Because if it was, then the probability of getting a dime on the second could be 1/4 or it could be 2/4, and it can't be two different things, right? So in other words, this depends on what happened beforehand. So this is a conditional probability. All of these are conditional probabilities on the second set of branches. I didn't leave very much room on that one. When you do it, you can do it much neater than I. All right, so this one, it's conditioned on D1, right? We came down the D1 branch, so we want to know what's the probability that the second thing is a dime, given that the first thing was a dime. This is N2. This is D2 given N1. And this is N2 given N1. All right. So now we have this whole diagram filled out, and we can answer lots of questions. All right. So for example, what's the probability the second is a nickel given the first is a nickel? So hopefully you can go in here. Second is a nickel. That's second is a nickel given the first is a nickel. That's the symbol. Oh, we have it right here, 2/4. All right, so this one, A, was 2/4. What's the probability the first is a nickel and the second is a dime? Well, there aren't any ands on this, right? So if we're going to do part B, we want the symbol probability that the first is a nickel and the second is a dime. I'll kind of separate this out. All right. Well, the first is a nickel and the second is a dime is this branch, right? This bottom branch, this one, and then going up here. But notice, I mean, those two, right? Neither one of those is an and. Well, this is where we would go up to this formula at the top of the page, right? So N1 and and D2, well, I have probability of D2 given N1, probability of D2 given N1, right? Oh, I don't need an equal sign there. I think I can erase this somehow. I don't know how to. Right, so D2 given N1, oh, and then I multiply by the probability of N1. Right, so the thing that was given. This is according to these formulas at the top of the page. Well, let's look down here. Oh, well, that's exactly the branches. So in other words, to get an and, you multiply down the branches. So probability D2 given N1 is 2/4 times 3/5, and that's 6/20. So I don't care if you reduce it. All right, so to get an and, right, an intersection, you can just multiply down the branches. You'll have exactly the right format. All right, you're going to get to try something here. We're going to continue. All right, the other big topic in this section is dependence, or independence, all right? You've probably heard a little bit about independence before. You'll have a pretty good intuitive sense of what this means. A and B are said to be independent. I think maybe the book gives you a little bit different definition, but A and B are said to be independent if and only if. That means this is an if-then statement that goes both directions. If the probability of A given that B happens is the same thing as the probability of A. In other words, it doesn't matter if B happens or not, all right, at all. Like, A is not dependent on whether B happens. The probability does not change if B happens. Similarly, probability of B given A is just equal to the probability of B. It doesn't matter that A happens, okay? So it doesn't matter, all right? Sometimes independence is confused with mutually exclusive events. So if you remember earlier, we had mutually exclusive events that we talked about. So I just want to look through this a little bit. So we know independence, the symbol for independence is that the probability of A given B is equal to the probability of A. Also, by the way, in your book, when you look up independence, it'll say that the probability of A intersect B is equal to the product of the probabilities. So if you've already taken your notes on this section, you'll have that one written down. Mutually exclusive events, the definition we had is just that A intersect B is empty. That's the definition of mutually exclusive. By the way, because of that, that means the probability of A intersect B would be 0. It's impossible, right? Remember we said the empty set is the impossible event. All right, so mutually exclusive means these things don't intersect. They can't both happen. Independence means, right, one does not affect the probability of the other. So here, down here on intuitive meaning, right, this means that one does not affect the probability of the other. Intuitive meaning of mutually exclusive is that they cannot both happen, or can't happen simultaneously. All right, but they can't both happen. It's either one or the other, all right? So in a diagram, a good diagram for mutually exclusive probably would be a Venn diagram where you have A over here and B over here, and they don't intersect, right? A intersect B is empty set. They don't intersect. Independence is sort of like if you're coming down, like you have A, and maybe you have like A and A complement, right, on a tree diagram. And then you have B and maybe B complement or something, right? You can have B or B or not B.